Hey everybody, welcome back to FRM 120. This is the second installment of the electrical lectures, the third lesson, but this is the second installment of the electrical lectures. And what I'd like to do is back up just a little bit and touch what we were discussing right when we left off in the previous lesson, bring it back up there, and we take off from there and start applying it to what we're about to learn. So anyway, we backed up, to where we have talked about our power generation, okay, where our power comes from, our three-phase and our single-phase. And we know that it comes from power plants, and we spin a rotor that has a magnetic field in it past these poles, these iron pieces with coils of wire wrapped around them, and anytime that magnetic field passes by a coil of wire, then a voltage is induced in this coil, and then we start generating power. In this case, we've got three different phases that the magnet is passing by, and so we are inducing three different voltages coming out of our power generator. Okay, now little fun fact stuff here for you. This generator, for example, there's several different power sources. We can have hydropower, hydroelectric power with water. We can have wind power with wind turbines. We have coal-fired power plants here in Western Kentucky. There are nuclear fired power plants throughout the United States. All of those turn that rotating magnet within the coils. And the way we do it here, the reason I'm bringing up hydroelectric power, we're not talking about sustainable energy and all that kind of stuff. But the reason I'm bringing this up is because we've got one over there by Land Between the Lakes. Okay, we've got the Kentucky Dam. Okay, so we've got the water that's dammed up, and it basically runs by a water wheel that's connected to to a shaft that turns that magnet that we were talking about right here. That's what's spinning that. Some form of prime mover is turning that rotor right there inside that alternator. Okay, and that's this right here. And these are the coils that we were talking about. These two things right here are depicting the coils right here. And as that rotating magnetic field passes these coils, it induces a voltage in the coils. The coils are connected to our transmission lines that go out, across our power grid. So that's how it's delivered. Now, like I said, this is just kind of a little fun fact thing. But here's the wheel on the bottom of a hydroelectric turbine. Okay, the water passes through. It's like these little cups, and the rushing water goes by through there and spins this shaft. And this is the same shaft right there, and it spins that shaft past these coils, and that's how the voltage is induced. And there's just another graphic where it's spinning that, and then again we step our voltage up. We're going to talk about that just a little bit too, and we put it out on the grid, out on the power grid. You see these lines that are going down the highway on these big towers. That's supporting these lines. Well, that's kind of where it generates from. That's where it starts, and it crisscrosses all across the United States and that stuff. But anyway, this is not about electrical and hydroelectric power, but I'm trying to give you some context as to, we're talking about alternators and things like that are in the power plants. Okay, with the coal-fired power plants, or natural gas, or even nuclear, this is sort of a mock setup for it. You have a fuel source, which, like I said, is going to either be nuclear, it's going to be coal, or it could be natural gas, depending on the price of the coal and natural gas before it goes on. But they basically create steam in this big, giant boiler type thing, and it creates steam, and that steam is delivered at a high pressure that spins this turbine, and look, it's connected to a shaft that's turning by a rotating magnetic field inside these coils, inducing a voltage in the coils. The voltage is then put out on our transmission lines, and off she goes into our homes, businesses, and industry. So that's a different way of turning this magnet. That's all it is. Okay, but you drive by these plants, and sometimes you don't even think about what they're doing or how this power comes about, this, that, and the other. So I just thought I'd throw that up there for you. And this is what you look inside of a power plant. Even here in Western Kentucky, this is the generator that's housing the rotating magnetic field inside the coils, and this is one of the big turbines that is spun with the steam that's either created through nuclear, coal, or natural gas. Okay, that creates the steam, and the steam comes across these fins and spins it, and once again, you're turning that rotating magnetic field inside the coils. This is an inside picture of a power generation plant. Okay, and then of course it goes out on our transmission lines that you see going down the highway. Again, we're not turning you into power engineers or electrical engineers or sustainable energy professionals or anything like that. Just kind of give you an idea of where this power we're talking about that runs our pump motors, that we transfer our mash with, and we move our grain with and things like that. We power also the heating elements in our boil kettles and our mash tuns and our hot liquor tanks and our boilers, okay, that even for those jacketed systems. So that's where the power comes from, and that's kind of what I wanted to kind of get at. This is about all we're going to talk about as far as power development, okay? So how does all this play into your world, okay? Well, we've got the generator that we've talked about. And of course, this is the magnetic rotating field inside these coils, okay? And this is technically an alternator, not a generator, but an alternator because it's creating alternating power or alternating sine waves, all right? But we create that, and then we hook it to our conductors, okay, 3 conductors, and we're over here spinning a motor that's inside our brewery. And again, it could be a boiler motor, it could be the boiler elements for the heater, it could be a mill, it could be a pump, anything. But this is a 3-phase motor, okay? Some of them are single phase, and we're going to get into single phase later. But what we do is we hook these 3 phases of voltage to our coils of wire that are in a circular pattern here. And this voltage right here will come through here, and it will magnetize this iron piece right here and this one here as well. This phase will magnetize this coil of wire and this coil of wire, and then this phase will magnetize this coil, and these coils create magnetic fields, and we have a rotor in the middle of it, okay, and it wants to align itself with a magnetic field, all right? Well, if the red magnetic field is strongest, then that rotor is going to align itself with that. As the red fades off and the green field starts to, or the green phase starts to build, it will align itself with the green one, which is a different color here, but it will align itself this way. And then as the blue one builds in strength, these magnets will be the strongest, and it will align itself with this. And it continues in this circular pattern, okay? And we create a rotating magnetic field. Now, this is the inside of a motor with the stator windings. I'm going to show you these windings here in just a minute. But what happens is when we have the 3 phases of voltage on here, we have a rotating magnetic field, all right? And what happens is we put a shaft in there that's got that magnet, this permanent magnet right here, and all it does is it chases that rotating magnetic field, and it goes around and around. It's literally chasing the magnetic field. If that magnetic field were to stop, that shaft would stop, but it continues to rotate inside that coil of wire, the stator right here, which is coils of wire, and it rotates around and around. Now I've got an example here, okay, and we're talking about connecting our conductors to our coils of wire. Well, what does that mean? I'm going to show you here in just a second. But I can take this apart and demonstrate it like here. So here's our rotor. It's magnetic, okay, and is attracted to the magnetic field that is rotating inside this housing, inside the stator, okay? The stator is the outer windings, okay, of the coils of wire, and this is the rotor, okay? It sits in a couple of bearings, and it rotates, and it chases that magnetic field around and around. So that gives you an idea of how that motor spins, okay? Now, when I say coil, what are we talking about? I'm talking about coils of wire and things like that. Well, a coil is literally, first of all, these are the coils right here in the alternator, or the power generation plant. Those are the coils that are spinning, and then of course, these are the coils in the motor that I just showed you when I had that motor apart, okay? But what do we mean when we say coils, okay? A coil is literally, this is real important, a coil is literally one piece of wire with a beginning and an end. That's it, okay? One thing to remember, when we're talking about 90% of what we're going to talk about as far as electricity goes is about creating coils of wire and putting voltage on them creating magnetic fields, okay? But we start with a coil. There's nothing magic about this. This is a beginning and an end. We don't want any breaks in here at all. Okay? It's one piece of wire with a beginning and an end, okay? Just like the spools of wire you buy at Lowe's or Home Depot or anywhere else. It's a coil of wire. That's all it is. Okay, it's wrapped around in a circle, and that's a key right there. Now, if we take this piece of wire and we wrap it around a piece of iron, okay, ferrous metal, all right, and then we hook it to a voltage source. Now, it can be AC or DC, but in this case, we're talking about AC. We hook it to a voltage source, it becomes magnetic or magnetized, okay? And it's like I've got an iron railroad spike, okay, well, I put the voltage on there, and it's going to attract anything ferrous metal, made of ferrous metal. So we've got a magnetic field set up inside this piece of iron right here. So this is kind of like one of the motor coils that we saw that are in circular pattern, okay? We put our voltage to one coil. This could be representative of the rotor, okay? It's attracted to it. And then when we have other coils that the other voltages are hooked to, then they become magnetized as well. And that iron core of that rotor is, the ferrous metal part of it is going to be chasing that magnetic field. Okay? Now we can do this with a DC voltage source as well. And we use this, but not so much in power generation. Okay, and I'm going to explain all that a little bit later too, particularly when we get to transformers. But it can be done with DC power. Okay, it is also attractive. Kind of like the way I did that, didn't you? I did. But anyway, we're going to stick to the AC and being our power source right now. And here she comes again. All right, so we've got that established that we put voltage on a coil of wire. We create a magnetic field, and what is inside that coil of wire becomes magnetized. All right. So as we are passing a permanent magnet or a rotating magnet, field past these coils, we are creating the voltage, and we are then hooking it up to our different coils inside of our motor, the one like I showed you earlier. We're connecting it to the coils, and they become magnetized, and that rotor wants to chase the strongest magnetic field. Well, the strongest magnetic field is constantly changing. It's changing based on whichever phase has the peak voltage at that particular instant. So it never is satisfied with one. It's chasing them all around, okay? It's just going from one phase to the next, one phase to the next, and goes around and around the circle, okay? Now, just some quick terminology. I ran some stuff by you. We talk about windings and coils. They're the same thing, okay? You can refer to them as windings or coils. Most of the time they're referred to as windings, but we call the stator is the outside, okay? This is the stator, okay? And you'll notice this is copper right there. It's copper wire, okay? Lots of coils of wire. And here are the ends of those wires right there, okay? I'll show you a little bit later, but each one of these is representative of a coil. The beginning of one coil and the other side of that coil, the end of it. Okay, you got multiple coils of wire in here, so you got multiple leads. Okay, the various ways to hook them up to our power source. You got to make sure you get that right. But this is our stator. Okay, and this is our rotor. This is the shaft this is magnetized. Okay, and it wants to be attracted to whatever magnetic field is strongest at the time. There's a cooling fan just to keep it cool as it spins, because you are creating heat. Because the electrons have been converted into rotary motion. That is a form of work, and work creates heat. Okay, so and you got a couple of bearings, and of course the shaft or whatever you hook up to make it run, whether it be a pump, fan, whatever the case may be, conveyors, whatever. If you're in your bottling and canning operation. Okay, but that is the inside of the motor. Just a little quick terminology, a bigger picture for you. Again, but the same thing. Okay, now there are two things that determine how fast that rotor is going to spin, how fast that shaft is going to spin based on the speed of that, the rotating magnetic field. Okay, we can vary that a little bit, and we can vary the speed. But one of the two things that determines the speed at which that shaft will turn is the number of poles that are in the stator of that motor. Okay, now I'm going to run back to this right here. We're talking about This is a set of poles right here for this set of windings. This is a set of iron poles for this set and for that, okay? So the number of poles that you have in a motor determines the speed at which it turns. Now, there's a formula for that. We're not going to learn the formula. You don't need to know. All you need to know is that you can have various speeds so that when you replace a motor, it does need to be the same RPM, okay? And that's determined, number one, by the number of poles in a motor, okay? So the more poles that you have, the slower the motor will turn and the higher the torque. I'm not going to really get into that a whole lot. Just know that the more poles you have, the slower the motor and the higher the torque, the more horsepower it can deliver. The fewer the poles, the faster that motor will spin and you'll have less torque, okay? So that's one of the things that determines the RPM of your motor is the number of poles in the motor. Now, here's another illustration of this motor. Okay, you'll notice all of the red coils, they are 90 degrees apart from each other, but they are all part of that one piece of wire. One piece of wire goes in, wraps itself around here, then it will wrap itself around here, then around here, and come back out. And you'll have the two leads for that one set of windings, okay? That one winding has beginning, round and around and around those red poles, and an end. Then you've got another set of windings, okay, that will hook to another phase of your voltage, and it'll come in as one wire and go around and around the C2 pole, the C2 pole, the C2 pole over here, and the C1 back here, and it comes back out. Remember what I said? A coil is a winding that is one piece of wire with a beginning and an end. There's nothing magic that's going on inside here. It's not connected in all kinds of different crazy ways. It's one piece of wire coming in and going back out, okay? And those are what you hook your two leads of voltage to. All right, same thing with that third one. It's the same thing, okay? So the four-pole motor, this one here is 4 poles, and each one of the poles for a phase is 90 degrees apart. Same thing with the B2, okay? They're offset a little bit, but they're still 90 degrees apart, and there's still 4 poles. 4 poles is the most common configuration for a motor, and that will run at about 1,800 RPMs, okay? So again, the speed at which a motor runs determines the number of poles. If we had 8 of these for each phase, then it would run a lot slower. Okay, it would run half the speed, and it would have a lot more torque. If we pulled 2 of these out from each phase, it would run twice the speed with less torque. Okay, so just let you know that the number of poles is one of the things that impacts the speed of the motor. Okay, so again, we've seen this before, and I need to go into this again. The other thing that impacts the speed is the frequency of the voltage going in, okay, into the motor, all right? And this is where most of you will see a variable frequency drive, or VFD, in a brew house, okay? A couple of different places. Number one, for some of our bigger breweries or more advanced systems, such as Dry Ground and also Hopkinsville, they have variable frequency drives on their rake and plow system, okay? And they also have variable frequency drives on their pumps. That's so they can control the speed at which the rake and plow mix up the mash, keep the mash mixed, okay? And also the rate at which they transfer the flow from, say, mash tun to boil kettle, or boil kettle to fermenter to bright tank, whatever. Okay, you don't want to just go full bore with your transfer, okay? For those that you should know by now that this is a very controlled process, and you don't want to, there's various reasons why you don't want to just go full bore with everything, okay? So, but this is varying the frequency of the motor. Now, we're going to get into VFDs later down the road, but that is the second way in which you control the voltage of, control the speed of the shaft of the motor, okay? So, again, we spin this magnet here, or this rotor inside our generator, okay, and that determines the frequency, okay, at which our motor receives the voltage. All right. Now let's talk about frequency for a second. This is the cycle, okay. There's a number of cycles here. So a cycle is a sine wave. We've seen the sine waves before, okay. Same sine waves right here, okay. The cycle is from the time it leaves a point, and this particular point is 0 voltage point, and it goes positive through the 0 point again to its negative full voltage, and then back to the 0 point. Now, it could be between the peak, from the positive peak, negative peak, and ending back up here at the positive peak. That could be one cycle. But this is one cycle as well. Okay, so we call this one cycle. This is one complete revolution of our rotor. Okay, one complete revolution of our rotor in our power generation source. All right, or our alternator. All right. So when we say frequency, though, frequency is the number of cycles that we have in a 1 second time period. Okay. So in this particular case, I've just got this up here. This is 1 second. So this is one cycle in there. This is 1 hertz, because frequency is expressed in hertz. H-E-R-T-Z, okay, or often designated as capital H, small z, hertz, okay. When you go to your homes, okay, pick up, open the door of your microwave, or look at your refrigerator, look at a hairdryer, anything that's electrical that will have it on there listed as needing 60 hertz of power delivered to through the voltage source in order for that appliance or device to work properly as it should. Okay? The reason there's a difference is because in Europe they run at 50 hertz, meaning that their rotation of their generators is 10 hertz less per minute, okay, or per second, excuse me. So it basically is the number of cycles within a 1 second period, okay? And in the United States, we produce our voltage at 60 hertz, okay? All right, and every time every time the magnetic field passes one of the coils, and then comes to 180 degrees from there to here, that is one cycle, okay? Well, it passes 3 different sets of coils in that alternator, so we have 3 different phases, okay? And all 3 phases in the United States are produced at 60 hertz. In other words, it spins at 60 times past each one of those magnets, these magnetic coils. It passes each one of those magnetic coils 60 times a second. This is where we get 60 hertz. Now, the more we cram in there, the more our frequency is, the higher our frequency. So if we get more and more cycles, these are cycles, we start cramming more and more of these cycles in here, our hertz value goes up. Okay? Now this one doesn't show the full 60, it goes up to about 5 hertz or so. But we cram 60 of those into a 1 cycle, in 1 second period, and we get 60 hertz. Okay? And so that's how we are creating 60 hertz, because that generator, remember the one that's spinning at the power plant, the hydropower plant and the nuclear plant and all that stuff, okay, they're turning that rotor at 60 hertz. Now they have a very, very precise control of how fast that spins, because we just can't let water just rampantly run through there and just let it spin at whatever RPM that water flow is going to be. We control that with, there's a lot of control mechanisms there that keep that rotor spinning at just the precise RPM, so that we get 60 hertz on the money. If we didn't get the 60 hertz, a lot of our appliances would just be all over the place. Classic example, during the ice storm, there were some folks that I had come out and I hooked up generators, and it's hard to regulate the frequency of a gasoline-powered generator. There's so many factors that kind of take away from how precisely it can deliver 60 hertz. A lot of times it'll be 65, 66 hertz, sometimes it'll be lower. But what I saw, and when I hooked up these generators, is I would measure the voltage and look at the sine waves as well. It'd run about 65, sometimes 70 hertz, depending on the load. Okay, if you load that gasoline motor up, it's going to slow this rotor down a little bit. Can't turn it as fast, so our frequency comes down. So you got a lot of variation. So what we saw, though, is like on microwaves, for example, the clocks, they were always running fast because they're designed to run at 60 hertz and keep accurate time at 60 hertz. You increase the frequency of the power coming into that microwave that you got plugged in, okay, you run your house through that generator that's sitting out in the yard, you increase that frequency, then you're going to impact the functions of that microwave, okay? The table's going to spin faster, just a little bit. The clock's going to run a little faster, or it could run slower. But I saw that a lot during the ice storm over the last couple of years when I've hooked up generators for people. Actually, I hooked up alternators for them, okay? And you know why now, okay? But that is how we create 60 hertz for the U.S. power grid. There you go. How you like that? That's me. Not really. But anyway, so the 2 things that determine the speed of the motor, the number of the poles, the frequency at which of the voltage going into the motor, and the number you're changing on the transfer pump, for example, you're actually changing the output frequency going into that motor. Here's a little fun fact that you're going to learn when we get into variable frequency drives. We can take 60 volts of input power coming into our drive unit, okay? We can take 60 volts and we can get as much as 90 to 120 hertz coming out. In other words, we put 120 volts at 60 hertz coming in, we can ramp that up to 90 to 120 hertz. How, you ask? We'll get into that later. It's really kind of cool. It's very cool, actually. But anyway, that's what I've got for you right now. Kind of want to take a break right now. So just review anything in this video you need to, and then come back and we'll watch some more as we go into the next installment of this particular lesson. Thanks for watching, and we'll talk to you soon.